I'm sorry, I don't know what happened. Can you hear me? Doesn't work. You can't hear me, or?
I can hear you, Karina. Can you hear me? I think we lost the connection to the meeting room. So maybe they will come back.
Ah, I see.
Yeah.
Okay, it was not me.
Yeah, no, I think it was all of us. Yeah. So.
Okay, was a cut.
Yeah, I think so. Yeah.
Hello, hello. Can you hear us online, Karina?
Yes, I can hear you.
Okay, perfect.
Okay.
Okay. So you can hear us, right, Karina?
Yes.
Okay. Good. We're sort of back.
Okay.
Anyway.
Yes, I
yeah.
was just typing the answer, but I will just say it then quickly if you have still time. So,
Yeah.
I mean, these are just my thoughts, but it's up for discussion. But I think it would be really interesting to see whether this community would put together the force at international level to look at the global SST change, how one would calculate it, also with respect to the uncertainties. So many of the time series, also for the global surface temperature, there is no uncertainty provided. Then we have also this aspect of regionalization. How do we report on SST, for example, because the satellite altimetry is starting in the 80s, but there is a reporting with respect to climate on a reference baseline, which is starting in 1880 to 19, and so on. So there are many questions, I think, in the style as, for example, Peter Thorne is doing on a 1.5 degree. But how do we think as a scientific community? Should we report on SST changes globally? In which context? Also, then, for example, with these questions on surface temperature rise, but also with respect to the needs at regional levels. But in order to support other aspects like adaptation, mitigation, etc., and uncertainties. But again, it's up for discussion, and thank you for the opportunity to provide this message here, because from a reporting point of view, it's very difficult and I struggled a lot.
Okay. Thanks very much, Karina. I think that's really valuable input, and I'm sure we'll take it up in the discussion later and to see how Chris can contribute to that. So thanks again for your input. So okay, I think let's move on to the next presentation. If technique is working, I don't know, Asta, if you can, or if we should share the presentation. Anyway, it's Andy Harris talking about using SLSTR as a reference sensor for global SST analysis. Not sure if I can help.
Is that good? Good enough.
What we need to you know how to share, Esther? Oh.
Well, click on that one, isn't it there?
Take it easy. No tripping.
That's it. That'll do, right? Start from there. Oh, what else do you need to do?
Excellent. Thanks.
Good.
Mm-hmm. Go ahead, Andy.
Oh, I see. Okay. And then. So this presentation is about some work that's been ongoing for the last couple of years, exploring how well we can actually use SLSTR as a reference sensor for global sea surface temperature analyses. I've basically been working as part of the NOAA EUMETSAT Science Cooperation Plan. It's been funded for the last couple of years, at least on my side, by NOAA STAR. And I've been working with Gary and Igor and Anne. And just very briefly, why do we use sea surface temperature analyses, level 4 products? They're very convenient. Users love them. I don't know if you can remember Shaquila's presentation yesterday, but she showed that the geopolar analysis had the most independent users of any OSPO SST product they produced. And it's a single 18 megabyte file per day, distilling down hundreds of gigabytes of data, essentially. And there are various flavors of these. NOAA has about 4. Various other institutes produce them as well. The geopolar, which is the one that I'm basically sort of responsible for, I guess, assimilates, a large number of both low Earth orbit and geostationary operational sensors. And comparing it with the OISST, you can see an improvement in resolution from the kind of 1/4 degree down to the 20th degree. And people really like these products. Geopolar is used as the source data set to drive the Coral Reef Watch thermal monitoring. This is a gratuitous slide showing the sorts of features that you can see from a kind of modern analysis like this. So it looks really nice in the mesoscale, and obviously oceanographers love it. Question, of course, it looked great, but how accurate is it really? Of course, we've got millions of satellite observations going in. They completely dominate the record. In fact, we don't assimilate any buoy data at all in our geopolar, but in reality, there's only a few thousand buoy observations per day. But the satellite observations are not measurements, they are retrievals. And so the retrieval process is slightly nonlinear, and they have spatiotemporal biases typically, and traditional correction for something like the daily OI will use widely spaced in situ. You can see here the drifting buoy data for one day. And you can see there are some areas that are very tight, but there's large areas that you could go to you could find somewhere that would be 1 million square kilometers with no buoy data in it at all. And so your ability to resolve fine scale bias corrections is very, very difficult. We have tropical moorings, which don't help a whole lot. Coastal moorings, very useful for the US and a few other places. And then we've got Argo floats, which maybe would help a bit if only they surfaced every day, but obviously they're down. You have 4,000 of them, but actually in reality you only get 10% every given day. So the question is, can we use a sensor like the SLSTR as a high quality reference to sort of fill in far more data? So essentially, when I said that the retrievals have spatiotemporal biases, we're kind of hoping that SLSTR doesn't, or at least it is well constrained in comparison to the standard sort of operational sensors that we have. There's already been a fair amount of discussion about SLSTR. There are 4 algorithms. There's 2 nadir algorithms, which have the wide swath, and then the dual view data comes from this 740 kilometer swath combining the nadir and oblique view. So in the nighttime, we have a 3-channel dual view algorithm. In the daytime, we have a 2-channel dual view algorithm. And I'm just going to flick quickly through these. These are the old versions of the algorithms. I just want to get really to the spatial biases that we get for the new day 2 SST algorithm. This is the algorithm coefficients, I should say, in this data set, this particular one you're looking at right here. And you can see that essentially if we go back, we just remove a little bit and everything's just got a little bit better. And then for the daytime, that has also got slightly better, and we can look at it a little bit more closely if we look at the old pre-adjusted day 2 coefficients. The problems that they had, I think basically they were sort of essentially RTM stroke spectroscopy type issues, and it was well known that the nadir 2-channel algorithm had significant water vapor bias. And with the new coefficients, essentially it goes away, so it's nice and flat. Now, although the recommendation was don't use the nadir 2, beyond 35, kilograms per meter squared of water vapor, there was a knock-on effect of this spectroscopy issue in other things. So here's the nighttime 3-channel. The revised data does this, so it puts that back onto the line. And if we take a look at the dual view, now the dual view is nice and robust, generally speaking, to spectroscopic issues, because half of its information is derived essentially from a geometric path length change, which is, 55 degrees is 55 degrees. It doesn't matter whether or not you get the spectroscopy right. And so that gets adjusted back onto the line with the new algorithm. And then same with the dual 3, that comes onto the line as well quite nicely. So what about other things like cloud detection and stray clouds? So there's a hint in the old that there is some residual cloud detection. Now, with apply the new coefficients, things have tightened up a little bit, but there's still a little bit of a trend now. This is not the new day 2 cloud screen that we've been looking at. This is kind of old results, but really the point still remains. But the interesting thing is, if you take a look at the trend with respect to for the dual 3 algorithm, you see that there's not much of a dependence at all. It's pretty flat, and it just adjusts back onto the line. So it looks like particularly the dual 3 algorithm is a very nice algorithm that can essentially cope with not just, variations in, say, water vapor and so on, but also it's quite tolerant to residual cloud. So that makes it quite a good candidate. And you can see this rather obviously, the dual view algorithms, depending on where you are in the world. So this is northern Indian Ocean. Basically, you have dust coming off the Arabian Peninsula, and you've got a substantially warmer retrieval relative to Ostia for the dual view track that you can rather obviously see. It's that one, isn't it? Kind of up here. So there's the dual view area, and then we go off to the nadir view, which is essentially a little bit aerosol contaminated in comparison. Now, we do have to worry particularly about aerosols as a source of bias. This is the VIIRS 2.8 product, which is the current operational one. For 3.0 is coming. But you can see daytime biases off Africa, and again, coming off the Arabian Peninsula, you see these aerosol biases, cool biases. And even the nighttime sensor, which has these, has a little bit less effect due to available the 3.7 micron channel. There are still aerosol biases present. So, how to estimate bias using SLSTR? So, I took the geopolar code, and instead of running at 1/20th degree, I reconfigured it to run at 1/4 degree, because I'm not going to analyze biases at 1/20th degree. I'm looking at a couple of test data sets to compare the dual view data against. So we have basically METOP GHRSST, and then we also have the VIIRS. So that's one morning and one afternoon polar orbiting sensor, and of course you've got this similarly, in nighttime as well. And so the differences are super-obbed at 1/20th degree. So I do not allow data to, I'm not matching a VIIRS sensor over here in this cell with an SLSTR over here. I make sure that they match. And then those data are then collected on the 1/4 degree grid and then analyzed. Now, you may remember before that I said that there were 3 stationary priors. It was flashed up briefly on the screen. And so instead of being fine scales, because it's a much larger problem, essentially the smallest correlation length scale is now 2 degrees and expands out to 12 degrees. So essentially, if you've got a lot of data, you'll get a bias correction that's roughly 2 degrees resolution. And then if you don't have very much data available, it'll be spread out all the way to 12 degrees away. And then it's gradually relaxed back to 0, essentially, by a factor of 0.9, which I think is rather similar to what Ostia does. Now, before I had been looking at the day one and then day one with updated coefficients, which is the stuff you saw. And now I'm looking at what the new day two stuff is that's available. There's updated cloud screening, as you've seen, and I said there's cloud changes to the quality level logic, and Igor then clarified this morning that it is still subject to tuning. So, you know, it may improve a little bit more, and that may go towards answering a question that I'll pose later on. I'm using the neural time D2 product. There was a test period that we had identified before with a really nice aerosol plume going across the Atlantic, but because they've not been able to reprocess just yet, I was taking the neural time data, and by happy chance, I received an email a couple of weeks ago saying, NOAA is tracking an aerosol plume. Look at this on the go. I thought, oh, well, I'll have those data. So that's the data I analyzed basically about a week ago. And so what we're looking at here is the previous product at quality level 5. I'm going to say previous, I mean old cloud screening, but new coefficients, and then the new day 2 with the new cloud screening at quality level 5, and then also what happens when you drop the quality level to 4. So this is the sort of bias that you get with respect to SLSTR METOP C right at the beginning of the sequence, May the 10th. And so those are the biases you see with respect to the collected SLSTR day and night, central 3A, central 3B. And that's the estimated bias field you get from that. You can see some aerosol off Arabia, a little bit of aerosol coming off Africa as well. That's the results of correcting the data. It's gone green. Oh, good. That's what it's supposed to do. And that's where we came from. So this gives you an idea. If I flip backwards and forwards between the two, you can see the amount of contamination that's been removed. Move to the nighttime product, something similar. That's the estimated field for the metopsy nighttime. Again, that's the correction value, and that's where we came from before. So that's the amount of bias that's been removed from that product. If we go to NOAA 20 for the nighttime, we can see a different bias correction field, but again, you see the aerosol plume a little bit off Africa and a little bit off Arabia again. That's the corrected field. That's where we came from before. You can see, and generally, the biases in V is a little bit less, which is what you'd expect. It's a more modern sense. It's a better product. And then we switch to the daytime, which is a little bit more interesting, perhaps, because you cannot use the 3.7 micron in the daytime, or at least it's not used at the moment. And so you see larger aerosol biases, particularly off Arabia, and that's due to the nature of the algorithm and the absorption properties of the aerosol. And that's the corrected value. And that's where we came from before. So again, you can see as I flick backwards and forwards the amount that's been removed. Go to the next day. There's been an evolution of the aerosol plume. It's stretching across the Atlantic now, and there's a sort of even more, I would say, in the northern Indian Ocean. That's what's been taken off again. That's where we've been. That's where we were. That's how much is removed. And so without further ado, these are the bias patterns for the old scheme, but new coefficients. And you can see aerosol plumes propagating across in both data sets, or all 4 data sets, NOAA 20 day, NOAA 20 night, METOP-C day, METOP-C night. Now, of course, the NOAA 20 data, it's in the afternoon, so you'll see more diurnal warming. So you tend to get more kind of linear structures also appearing in that data. But overall, you'd probably say that leaving aside the diurnal warming, the things that stand out are the noise in the METOP-C correction is a little bit larger, which is not too surprising. And also there's more aerosol bias visible in the daytime than the nighttime. So if we switch now to quality level 2, or rather the day 2 quality level 5, biases that are being observed here in this are actually somewhat larger, I would say, and it's not just here. I would say also the stuff that's going on around, essentially down at sort of 60 degrees south, basically near Antarctica, they're a little bit more intense as well. And also the overall structure is just a little bit more noisy. And then if we go a little further again, if we go to dropping the quality level to quality level 4, we get even more, I'd say, noise, but we also get more intense estimates of the bias correction field. So that bit where you see these, where it goes blue and then it goes white, that's where it's capped out at -2, essentially. So the corrections for those areas where you see it, the white patches are actually at -2. Okay, that's fine. And so let's flip back again and just look at the NOAA 20 for those 3 different things, and you can see we have the day 1.5 thing, which is a little bit less noisy, and then the day the day 2 quality level 5 and quality level 4, and you can compare the kind of noisiness and the intensity of the bias correction fields are being estimated depending on which quality level and which data set you take. Now I'm going to skip over this one because what I really want to get to is here we have the day 1 versus day 2 coverage. Now, I was going to point the finger and say this simply we're missing some orbits, and that may well be true because this is a near real-time collection for this. But also Igor was showing substantial changes in the coverage for his day 1.5 to day 1 to day 2 algorithm anyway, so I reserve judgment on that. And then if you drop to quantity level 4, all of a sudden for this day, you get this huge anomaly essentially here showing up, which is essentially, I think it's sampling an aerosol field. Now, but if we look away from that, day 1 looks like that, day 2 quantity level 5 looks like that, and you can see these little speckles of kind of warm and cold in there. And if we go put to quantity level 4, even more speckles have turned up. So there was a price to be paid for getting more aerosol in that we're also including other things which look like they're probably due to cloud edges and something like that. So some sort of smart way of removing that would be good. This gives you an idea of the sort of effect on the bias field. And one of the things to note here basically is that if we look, there's an example of the kind of missing swath. You can see those warm kind of features that are appearing depending on whether or not you have data. And that's the new day 2, and that's the day 2 quality level 4. But it didn't have a huge effect here because this is daytime SST. So if we take a look at nighttime SST, it turns out that it does have an effect because the nighttime SST cloud detection isn't got the visible channels, so the VIIRS data is not picking up, is not screening out those data. And so this bias correction has a significant effect at night, which is important because nighttime SSTs are generally regarded as more accurate. And you can see that, okay, so we can see essentially here the effect of applying a quality level 4 at night. You'd really like to be able to get rid of that large aerosol bias if you could. My conclusions are here. It's a very useful sensor to use. The fact that we've got 2 platforms does help to fill things in. You've got to work out exactly how best to use this as a reference sensor. Things are getting better all the time. I look forward to seeing the kind of improved tuning, and then also to try and consider how to remove, trying to put all of this at the moment, we're doing it on statistical methods. And we've got a presentation. Chandra's giving a presentation tomorrow morning, first talk after coffee, which is to see if we can actually try and estimate these biases kind of at source, and then we'd hopefully be able to apply these statistical methods to deal with the residual. That's it. Thanks.
Thank you, Andy. Let's take the next presentation and then questions. And the next one is Pia Englyst from DMI, talking about the global satellite sea and sea ice surface temperatures since 1982.
Thank you, Jakob. Yes, I'll just give a, there's an echo. Andy, echo. Problemer. Der er et echo. Okay, that's how it is. Okay, yeah, I will just give a brief motivation behind why you think this SST-IST combination is very important. One of the clear signs of climate change, that's the large reduction in sea ice cover in the Arctic. And that's what you can see from the graph to your right. You see here the monthly mean sea ice extent in September and March. And in both cases, you see a reduction, in particular during September. And that, of course, leads to more open water days. And that's what you can see on the map, where you see the trend in open water days from 1979 until 21. And there are some regions that are experience a huge trend in open water days, up to a month more of open water days per decade.
And that opens up for new possibilities, but surely also new challenges. And one of these challenges that is the surface temperature mapping in this region. Traditionally, sea surface temperature trends have been calculated using, or just for the extrapolar oceans, which is defined as the region between 60 south and 60 north, or using the so-called under ice SST, which is a proxy SST of, or is the water temperature just below the sea ice. And it's usually fixed around the freezing temperature of the water of about minus 1.8 degrees. And an example of how this is used is under ice SST to calculate the surface temperature trends. That's what you can see on the maps here. That's from the latest ocean state report. And you can see that there is almost no trends in the sea ice covered regions, which is expected. So this is fine as long as you know what you're looking at. The real problem arises when you take out this region and average the trend into an Arctic sea surface temperature and compare it to the global sea surface temperature trend, and you make it into the IPCC report stating that in the Arctic, the mean SST increase over the last 2 decades is similar to or only slightly higher than the global average. So per definition, a large part of this region has a constant sea surface temperature. So what we are proposing now, and what we have been working on, is this combined sea and sea ice surface temperature climate data record. It currently covers the period from 82 and up till 2024. And it has been developed as a part of the C3S. And as Jakob said yesterday, it was original replacement product for the CCI. It is also based on the CCCI level 2 and level 3U input data, together with the ASTI data that Vibke has a poster about, the level 2 ASTI data. And these input fields are aggregated to level 3S fields before they are entering the optimal interpolation scheme, producing the level 4 gap-free combined sea and sea ice surface temperatures with corresponding uncertainty estimates. And because this product was originally a replacement product for the CCI, we have sort of been benchmarking against the CCI in terms of validation. But we have also included this under ice SST to be consistent with the CCI products and other global level 4 SST products. And here we have used, and that's a work by Gisela and Alex, I think, who are both here today. The under ice SST is estimated as a function of the freezing temperature, which is a function of the salinity, and the sea ice concentration. And the coefficients, they have been fitted against GHRSST in the region from 0 to 15% sea ice concentrations, and they have been fitted for both the northern hemisphere and the southern hemisphere separately. And the map shows an example of the resulting SST field, including this under ice SST. And Joanna has made a spectral analysis of our product and compared that to the CCI, that's called Ostia here, to assess the effective spatial resolution. And she has used 10 years of data, and we can see from the latitudinal arid spectra that DMI, the C3S product, SST-IST product, that maintains a higher spectral power for the shorter scales, 60 to 10 kilometer length scales, while they agree pretty much on the longer scales. And that indicates that the combined SST-IST product are better at resolving the small scale features. In terms of validation, our IST components validate very similar to the Siemens product that Jakob presented yesterday, and also similar to the level 3 product that Jyvke has presented. So I'm not going to go into details with that. We've shown that before. And in terms of SST, you can see the mean validation results for the record in the table to the right against drifters, argo floats, moorings, and ships. And also you can see the robust standard deviations and the median difference over time for both the C3S DMI product and the CCI SLSTR that we have been benchmarking against. And we can see that in the early years, we have higher uncertainties as expected. But most importantly, we have a similar performance as the CCI product. That also means that if we are looking at the trends using our under ISSST, we also get a similar trend to the CCI product. And that's what you can see here with no clear trends in the CIS covered regions. But if we instead use our ice surface temperatures and calculate the trends again, we get a much different picture. We have differences in the trends of up to 2.5 degrees per decade by calculating the trends in these two different ways. And the question is if we can see these differences in the trends when we're looking at the global SSTs. And yes, we can. We actually see an increase of 40% in the global sea surface temperature increase if we use the combined SST-IST product instead of just the SST under IST product. So it's very important to have, or this data set brings some new information that are very important for monitoring of warming trends in the high latitudes. And it can be used for different applications. It can also be used to benchmark and evaluate reanalysis products and climate models. And this is just one example where our combined SST product has been compared with AR5 surface temperatures. And now we can do this globally, not only for the Arctic. And you can see there are quite large differences, in particular for the Arctic. And this is something we would like to look more into in the future, definitely. Yes, so to sum up, we have developed this new combined sea and CI surface temperature climate data record within C3S based on satellite observations only. And it will be available in the climate data store very soon, hopefully. And we can conclude that it's very important to include the CI surface temperatures because it results in an increase of 40% in the surface temperature trends, the global surface temperature trends. And we see the largest differences in the Arctic, where we also have the largest sea ice reduction. And we also have some improved sea ice surface temperature information. This is also the first global gap-free level 4 IST product. And that can be used to evaluate reanalysis and climate models. And the initial study that we have made indicates that AR5 is underestimating the warming trend going on in the Arctic compared to our satellite observations. So, for me, thank you.
Okay, thank you. And now we have a bit of time for any questions or comments or anything to the speakers. Peter.
Thanks, Peter Cornilland. And I have a question for Andy, wherever he is. Still here?
Andy's here. He's hiding up in front.
You looked at bias over large scales. You defined your bias basically as something larger than 250, I think is what you said. What I was wondering is if you had looked at the temperature difference, local bias, you looked at how much the temperature varies on the 200 kilometers. You used a 4 kilometer range, I'm sorry, a 4 Kelvin range in the scale, temperature scale. Suppose you'd use like a 0.5 Kelvin, seen a real lot of speckle, 200 kilometers there.
I mean, the analysis is, the bias analysis is run at 1/4 degree. The minimum correlation length scale is ±2 degrees. So you won't see a feature that's smaller than that in terms of smoothness.
Right. What I'm asking is how much speckle would you see whatever the smallest scale you have, you were to a much smaller temperature. At 4 degrees, if you'd use half a degree, you know, a lot of speckle.
I mean, no, because you can't. I mean, you won't. It'll be smooth over that range, so it won't look speckly. It'll just stretch it up, but it won't. The minimum wavelength of the features it can resolve is of the order of 2 degrees.
Okay, so
essentially.
Would you seen speckle at 2?
I mean, I would say that if you look closely, you do see structure. One of the things that I didn't do was if you blow up the, to give an illustration, that bit when I showed what happened, this was the difference, this is the estimated bias, this is what happens, you apply it, and then I flick backwards and forwards between this is where we started, this is where we finished. If you look in real close detail, what you'll see things like, for example, where there's a streak of diurnal warming, something like that, you'll find that essentially it's not perfectly corrected because the wavelength is, of the order of 2 degrees, but actually the sharpness of the bias feature for something like, diurnal warming is sharper than that. So it fails to correct something that's smaller than 2 degrees. So the speckle that you actually get is, you can see it in the input data. So you saw the speckled results, when I was showing what happens when you drop the quality level. So you can see it in the input, but once you've done the analysis, those features are essentially smoothed out.
What I'm trying to understand is if you have features that are 100 kilometers, right? If you have features that are like 100 kilometers that are actually due to the meteorology not being properly corrected, and those play a really important role if you're interested in mesoscale processes. Is there any way of characterizing those? Seems like you almost have the data to do it.
Well, I mean, that's one of the things, for example, with Sionju's presentation, is that we are using essentially higher resolution meteorological information. So you can resolve at a finer scale than that, but the way the analysis is running at the moment, the only way to do something better than that is to essentially drop the bias correction down, the length scale down, and run it at a finer resolution. But you don't really want to do that. It's kind of, I could add a 4th length scale in there. I could halve it again or something like that. But generally speaking, I'm not trying to map things directly from, if you go down to the pixel scale, you can essentially say, I want to bias correct to SLSTR, and all you're effectively doing is replacing with SLSTR, but that's not what you want to do, really. The observations are independent, so to some extent, you're trying to correct for something of around that sort of, 200 kilometers and above scale, and there are finer resolution features, but they won't be corrected by this methodology. This is still far, far finer than you can get out from something like a daily OI. The length scales in the daily OI for bias correction are of the order of maybe 15 or 20 degrees. You can see these kind of patterns in them. And so that, I'd say basically we probably improved the resolution. Where we have the data, we've improved the resolution by close to a factor 10 by doing it this way with a sensor that has the ability to resolve things, as opposed to just a point measurement from a buoy.
Thank you. Thank you, Andy. Any other questions? Chris.
This is to Pia. It looks very promising, the improvement in the length scales in comparison to CCI. But of course, having more power at a shorter length scale doesn't necessarily mean you're actually resolving features. Have you done any tests to show that what's involved at those length scales is actually real rather than, just noise at that length scale?
Yeah, it's actually Joanna who has done this part, and I'm not sure she's done more than this, looking at different regions and different years. Yeah,
Oh,
but that is something to look more into, for sure.
Good point.
Yeah.
Yes. another.
Yeah, Pia. Thank you for talk. I have a question about this ice surface temperature, because in Arctic there's a lot of different ice thickness, snow thickness, and actually in small area there's quite large variations in the surface ice temperature. But I cannot see such kind of change in your results. Any comment on this?
Like large spatial variabilities
Yeah,
in the surface temperatures.
yeah.
I'm sure we have that. I mean, maybe you can see it on Vipke's poster. I don't know if you have any examples from the level 3.
Okay.
Yeah.
Okay. Okay.
Yeah,
Check it
you will
out
see the
later.
variability.
Yeah,
Yeah,
okay.
if you look into the.
Yeah.
Thanks. I think there's a hand raise by Chongyang. Chongyang,
Yep.
feel free.
Hello. Can you hear me?
Yes, go ahead.
Good. So I'm just kind of follow up on Chris' question to Pia actually, or semi sort of suggesting a way to look into it is to. Sorry, this is Chongyan from Met Office. Sorry. So usually the power spectrum analysis, I assume that's what it's based upon, cannot resolve anything under twice the grid resolution. So I think I missed the bit on the introduction of the product, so I don't know what the grid resolution is.
Thank you for raising this. I don't think I mentioned, so apologize for that. It's 0.05. So
Okay,
around
yeah.
12
So
kilometers. So and that's where it dropped off around 10 kilometers, I think. Yeah.
yeah, so it's probably like so it's about 0.05, so that would be 510. Yeah, so okay, yeah. So I think that's probably I would say about 10K. Yeah, okay. I just want to figure out the information. Yeah, so and then I guess in terms of under that, and also depending on the actual like field that you apply the analysis on. So if it's has been regraded or not, that also makes difference as well. So but I assume you probably just download whatever available there. So yeah, that could especially in the finer scales, that could introduce some noise. But I guess that'll be quite small scale. So I assume probably 10K does look like sensible. Yeah, thanks.
Yeah, thank you. I agree. Yeah, Chris.
Thank you, Chongyang. Chris again.
Just another question. It sounds like the data set is ended at 2024, and that's going to be on the CDS soon, I hope, because I'm looking forward to get my fingers on it and using it.
Mm-hmm.
But are there no plans, no way it can be made, at least in a delayed mode, because it's a really important data set development, I think.
Yes, I can comment on that because I presented on Monday. It's part of the next phase of the C3S that this product will be produced in sort of delayed mode. So depending on when the contract is kicked off or is signed for the C3S, that's the plans.
Oh, great. So as soon as it goes up with the static one, it will then be updating in time, more or less.
More or less. I mean, after summer, at some point, yes, we will have like a monthly updates or production with a month's delay. Any other questions, comments? Or wanting coffee? That's also fine. Good. Let's break for coffee and let's see. Okay, we are and cake. Yeah, we are back here 20 to 3. Thanks. And thanks to the speakers again. Okay, if everyone get back to their seats and we'll start again. Okay, great, thanks. And let's resume this session with a presentation from Chris Merchant from University of Reading about sea surface temperature in deep convective areas. Go ahead, Chris.
Thank you. There was an echo there. Okay. Good afternoon. As we know, the Earth has been running at about 1.5 degrees of global warming for the last couple of years. And that's a surprise. We didn't expect global temperatures to reach that level until the early 2030s. Now, that's a sign that the Earth is warming up faster than it was. So the trend of warming is accelerating. Another way of saying that is the Earth is accumulating energy at a faster rate than it was. And we can see this in the Earth's energy imbalance. So these are two data sets that represent the difference between the sunlight coming in and the energy it carries and the radiant emission of Earth to space. And you can see that it's always been going up through this record since the 1980s. But in the last decade or so, the slope has increased. And that's what's driving this acceleration in the rate of the temperature change. Now, if you integrate this curve in time, you get the accumulation of energy in the Earth system. So how does that relate to sea surface temperature? Well, the simplest possible assumption we can make is that a constant fraction of this accumulating energy goes into the mixed layer of the ocean. That's not necessarily the case, but it's the simplest assumption we can make. And it turns out that that over the period of decades to decades is how it's been working, which we can see if we look at how global mean sea surface temperature, in the sense of -60 to 60 degrees, to avoid the problems that Pia has pointed out. You can see that over time, that the blue data are the blue lines of the data. You can explain a lot of that variability with just 4 factors. There's the Pinatubo volcanic eruption, there's the solar sunspot cycle, there is the effect that ENSO has on changing global temperatures, and there's one more, which is Earth's energy accumulation. That curve there is the Earth energy accumulation curve is the integral of the EEI that we saw in the previous slide. And you can see that it's quadratic, which is what you get if you integrate a straight line with a slope, of course. So underneath all the variability that we've been looking at has been this quadratic increase in sea surface temperature over the last 4 decades. Now, the Pacific is very important here. Obviously, it's involved in the ENSO phenomenon, but the reason that we always expected an increase in Earth energy imbalance is that the Pacific drives a certain aspect of the climate sensitivity. So when you've got radiative forcing on the planet, you don't get the full, that doesn't describe the full energy imbalance. Some of it's offset by how the Earth responds. And that response is very important in determining how the future will evolve. There are 2 explanations as to why the Earth energy imbalance has increased. One is that people have been cleaning up aerosol. That's true in China, and it's true in terms of shipping fuels. The other is that the climate sensitivity is somewhat changing, and that's the one I'm looking at in this talk, and that's all to do with deep convection and the Pacific Ocean. So deep convection is where there is strong ascent of the air, and it mostly happens in the warm pool in the tropical areas. You can see this is ECMWF's average vertical velocity, red is upwards. That happens where the SST is warmest. The plot below shows you the fraction of time a given location is warmer than 70% of the tropical SSTs. And you can see that that's focused on the warm pool. So that's where deep convection happens. At this point, I'm going to introduce a factor called SST hash. It's the difference between that warmest 30% of the tropical oceans and the average. And we'll come back to why that matters in a minute. The reason that Earth energy imbalance has increased from a sort of observational point of view is that the Earth has become less bright. The albedo has gone down. And that's mainly been happening in the Pacific Ocean. And this is one mechanism that's thought to explain that. So you can see that we have the warm pool, that's the warmest 30% of the ocean, and then the rest of the tropical ocean is, we're calling it the cold pool. And those two temperatures do different things to Earth's albedo, mainly by affecting the amount of cloud in the areas above the cold pool, which is determined by a capping of the boundary layer there. So when you raise both the warm pool and cold pool sea surface temperatures up, that tends to erode the boundary strength. You get fewer clouds and more light is kept within the system. If you just warm the warm pool up and not the cold pool, you get more vigorous deep convection. That shares its temperature with the upper troposphere in other parts of the world. That strengthens the boundary layer. You get more clouds and the albedo goes down. So that contrast between the deep convective area temperature and the rest of the tropical SSTs is crucial for determining how quickly the world is warming. So what I was aiming to do for this talk was look at how those two temperatures, the tropical average temperature and the warm pool rest of tropics contrast, SST hash, look at them in GHRSST data sets to see how uncertain or what the uncertainties are if we look across an ensemble of SST products. So here are the data. So there are two time scales here. I have 4 products in the upper plot, I think is, yes. No, 6 in the upper plot. And those are the HADDIST one, which is not a GHRSST product, but one we've often used, and it's in the GIMP and so on. OI, Ostia version 2, what we've seen mentioned a couple of times, CCI version 3, so Owen's latest release, the Muir and the CMC analyses, multiscale and Canadian. And then in the bottom plot, the 4 that last back into the 1980s of those, because Muir and CMC don't go that far back. So that's the raw data, that's the tropical average SST. We can see a bit more detail, of course, if we take out the annual cycles shown here. And here, those same data are plotted in terms of their difference from the ensemble mean, or a trimmed ensemble mean. So the outer 2 values are thrown away, and you take the average, so what's left. So that gets rid of some of the outliers. And we can see features that we're quite familiar with. We've been looking at GHRSST data sets over the years. The, for example, HADDIST has got a cooling trend relative to this ensemble mean. There are the well-known problems in OISST being very cold at the start and not quite that stable. If you believe that the trimmed mean is some sort of best estimate for the truth out of these data sets, it's the CCI that is the most stable, and that means Owen's done a good job. So thank you, Owen. So that's the consistency of the tropical mean. You can see that we have differences between these data sets, which are not huge, but then this is a large scale monthly value. And so when we're looking at 20th of a degree, that's not insignificant. That's a huge amount of heat, for example, represented by 20th of the degree. if we look at SST hash, which is remember the contrast between the warm pool temperature and the tropical average, we can see that in these data sets, the spread is, maybe 10% of the signal, and a bigger fraction of the variability in that quantity. So again, it's the same data sets, the 4 at the top and sorry, the 6 at the top for the shorter period, and 4 of those for the longer period. The differences are systematic here. We have CCI, CMC, and Muir looking quite consistent with each other, and other data sets show less of a contrast. And since this contrast is driving this tropical circulation, even quite small values of SST difference are important. Let's look at what I said about the decreasing reflection by tropical clouds. So these are series data again. This is the cloud radiative effect. So the impact on the outgoing radiation from having clouds in the shortwave. So this is the reflectance of sunlight. And you can see that this has been drifting up over time, also lots of variability. I'm going to show how the smooth curve here, which is a 6-month rolling average, relates to these two SSTs, the tropical average and SST hash. So using the 6 data sets I had, this is the regression of essentially the albedo of the tropics against those 2 SST factors. And you can see that just those 2 sea surface temperature factors explain a pretty good amount of variance in the tropical albedo, and therefore are predictive of Earth's climate sensitivity. But for the purpose of GHRSST, we're interested in how much agreement we have with these various data sets. Using the ensemble as a measure of the uncertainty in a very simple way, the uncertainties on the right-hand side are how uncertain the sensitivity between the measure of SST and the shortwave cloud radiative effect, how uncertain those are in terms of the variability. And the answer is pretty positive for GHRSST. I think we're less than 10% uncertainty arising from differences between data sets. And that's a pretty good result. We might want it a bit less because this is such a key climate parameter, but I think that's quite positive for looking at GHRSST data sets. And the same with SST hash, 5%. Now I had, for those whose favorite data set isn't here, I did as many as I had time to before I came to the meeting. And I apologize, I am going to add some more as I do this a bit further. I was also keen to dive into the daily data and see what's driving the differences that you can see here, especially the differences are mainly in the deep convective region. And of course, this is possibly the hardest. Okay, the warm pool and the high latitudes are the hardest areas in the world to get a decent SST, of course, because it's so cloudy, such a lot of water vapor. But that's all going to be future work. So essentially, I've explained that global SST is warming as part of the general warming of Earth at a faster rate due to increasing Earth energy imbalance. Tropical SST patterns are crucial in this area for modulating the climate sensitivity, and they do that by modifying the cloud feedbacks through the mechanism I explained. So in this business, the contrast between deep convective and tropical mean SST is critical. We've compared GHRSST data sets to one longer term centennial scale SST data set, and we see a bigger contrast than they did in HADIST. I've yet to look at the other centennial scale reanalyses to see whether that's systematic between satellite data and other sources. And the GHRSST data sets are coming out pretty well. We are seeing differences between data sets of order 10% of the variability of the relevant phenomena, which is a good result, although we might want to work on that further. The differences have noticeable but modest impacts on assessments of the coupling of SST and the parameters related to cloud feedback. So overall, that's a good result for our GRIS data sets. And if it's worth looking further at this to understand what our different products are doing in deep convective areas, because it's such a crucial part of the world. That's it.
Thank you, Chris, and exactly on time. Perfect. I think we'll proceed with the next presentation and then take questions after that. And I believe it's an online presentation. Boyin, Huang, if you are ready, we'll just set up here. Okay, we will share it, or?
I tried to share.
Yeah.
Have you seen my screen?
Yes.
Okay. So thank you. So my name is Boyin Huang. I'm going to present the extreme marine heat waves in the past decade. So this is a very kind of collaborative work among different units of the university and the NOAA different department. As an introduction, here the panel showing is that in the August 2023, the SST is very high over the North Pacific, Tropical Pacific, and North Atlantic. At that time, there's many kind of requests from public and news media about record-breaking SST and marine heat wave. The second panel showing the marine heat wave in August. You're seeing using the 90th percentile criteria. You're seeing a lot of marine heat wave activities over the global oceans. More important message here is if we look at the difference between the SST and the record-breaking SSTs, you're seeing the shaded regions as SST averaged during that period as a record-breaking status. So this means in August 2023, not only we have a very strong marine heat wave, if we look at the criteria of the record SST breaking, we call this as a super marine heat waves. So they have two criteria. One is the marine heat wave, another one is the record breaking status. So we create a name called the super marine heat waves. So this study is a further step about the supermarine heat waves, basically. We're still using the assay dataset from NOAA, NCI, DOISST, daily OISST, and we first introduced the marine heat wave criteria. I think maybe it's well known, 90th percentile criteria and 5 days extension period. Then we're using extreme marine heat wave. So using a higher criteria, 97th percentile. Then we're using a record-breaking SST we call the supermarine heat waves. So record high SST is defined a little bit tricky. For example, in 2025, the record-breaking SST is calculated based on the 1982 to 2024. So this means record-breaking SST upgrade progressively every year. So this is why we can only define supermarine heat waves after like 2011, because we need like 30 years base period to remove all these noises of the record-breaking SST as a reference. Then we calculate the dechanted marine heat wave. So everything is same except we filter or dechanted the SST during the period, like in this case is 1982 to 2024. So remove the SST channel first, then calculate the marine heat waves. We call it dechanted marine heat wave. Then we have a difference between this extreme marine heat wave and dechanted marine heat wave. We call this warming marine heat wave. So this basically the difference between the extreme and the dechanted marine heat waves represent the marine heat waves according to the warming trend. So we use the marine heat wave metrics. It's quite familiar. One is the intensity, basically the mean SSTs. We have the durations of the year, every year. Then we have frequency, every number of the events during the year. Then we have the area coverage. First, area coverage is based on the daily marine heat wave activities and associated with the total ocean area. Then we further averaged into monthly coverages and annual coverage because metrics of marine heat waves basically is based on the annual metrics. So this the area coverage is a little bit tricky. And then because of the different features of the intensity and other metrics, we think it's very fair to integrate all these metrics together into a cumulative intensity. The major objective of this study is one is to study the marine heat wave variations according to different criteria threshold, and then we focused on the impact of SST warming trend and the record-breaking SSTs on the extreme supermarine heat wave, supermarine heat wave, and warming marine heat waves. Here is an example of the different lines representing the different marine heat criteria. Like, for example, red represents the record-breaking SST with the different seasons. If we pick a typical point like in Eastern North Atlantic in 2023, we're seeing that temperature is very high above the record SSTs, like in the June, from June to August, always to the all the way almost to the November. So above this red line, we're seeing that shaded red regions represent the supermarine heat wave activities during that time and that regions. Then first we look at the evolutions of mean SST and duration, frequency, and area coverage with different criteria of the marine heat wave activities. So first of all, we see a very clear message that all these metrics have positive trend. So this means these marine heat wave in general with different criteria, they all increase with time. However, if you look at the SSTA magnitude and with other metrics, you're seeing the opposite directions. For example, SSTA is higher when the criteria is higher. But on the other side, the duration, frequency, and area coverage is low. So this distribution is quite intuitive because of the criteria feature. The question is, how do you quantify actually which one is stronger? In this case, it's quite tricky. So I think it's quite fair. We need a new metrics called cumulative metrics. We integrate all these activity marine heat wave events with time and with regions with different coverages, for example. So in this case, we similar to that one, we calculate the time evolution of the supermarine heat wave, extreme marine heat wave, and the descending marine heat wave. You're seeing the similar features of the different quantities or magnitude. For example, higher SSTAs for the supermarine heat wave, but lower duration and frequency and area coverage. For the extreme marine heat waves, the magnitude is SSTA magnitude is low, but the coverage, total duration, all these things actually is higher. So the fair thing is I propose that we should have a cumulative metrics or cumulative intensity integrated for, in this case, is from 2012 to 2024. You're seeing the spatial distributions, for example, in the first panel, extreme marine heat wave is very strong in North Atlantic, North Pacific, and Arctic region, and also strong in the Southern Oceans. Relatively weak for the supermarine heat waves because the coverage and event number frequencies becomes lower. So this is why all the SST magnitude actually is high. In compare with the descending marine heat waves, actually the spatial patterns are very similar. So that's the only thing actually is not our focus. The focus is panel D. The difference between A and C represent the marine heat waves associated with the warming trend. So the key here is relative strength. So we look at the ratio between the supermarine heat wave and extreme marine heat waves. You're seeing the shaded, actually the highlighted color is in green is above 60%. That means in these green regions that supermarine heat waves in compare with the extreme marine heat wave is dominant in the North Pacific, North Atlantic, and many of the Southern Ocean regions. However, different patterns are found if for the warming trend, warming marine heat wave in compare with extreme marine heat waves, which is dominant in the tropical oceans, particularly in the Indo-Pacific Ocean, Western Pacific Ocean, and Western tropical Atlantic Oceans. So the reason of this warming marine heat waves activity is that on the right panel of this slide showing the strong SAT trend in the tropical oceans. So the other factor is relatively low of the extreme marine heat wave in the tropical oceans. For example, this slide you're showing the tropical extreme marine heat waves relatively have low magnitude in compared with high latitude. So this is why one is have a strong trend and then have a weak reference. This is why we have a dominant ratios in the tropical oceans. If we integrate over the global oceans, then in the unit of degree days, we found also increase with time in compare with other metrics we presented in the previous slides. So extreme marine heat waves is or kind of increase with time. And in compare with this extreme marine heat wave, we seeing the supermarine heat wave actually is relatively dominant in the early period, like before 2018. And after 2018, and warming marine heat wave and extreme marine heat wave are comparable, or they both are increased with time. If we calculate the trend or the ratio between the supermarine heat wave and the marine heat wave in reference to the extreme marine heat wave, as I said before, before 2018, supermarine heat wave is dominant. Seeing the ratio is much above the ratio of the marine heat wave. But after 2018, these both are become kind of equivalent or relatively similar magnitude. However, their trend is very clearly different. Supermarine heat wave, the ratio actually is decreasing, and the warming marine heat wave, the ratio is increasing. So the bottom line is here for the future. I believe the marine heat wave will be dominantly caused by the warming trend. Here is a brief summary. First of all, marine heat waves are increasing and with the different criteria. If using different steel, they have the increased tendency. And the marine heat wave, extreme marine heat wave presented here like 97 percentile, as well as the maximum SST we quantified as the supermarine heat waves happens in the past decade and the global oceans. There are many regions. It's hard to say which region is kind of happening of the extreme marine heat wave or supermarine heat wave. It looks like everywhere. And extreme marine heat wave, if you look at the period of 2012 and 24, mostly associated with the SAT warming trend and the cold breaking SATs. So if you look at the numbers, on average, you're seeing the warming trend may be smaller, like 40%, and the cold breaking is relatively speaking 50%. But if you look at the time tendency, you're seeing the warming trend is increased trend. So it becomes relatively becomes more dominant. And the cold breaking is become relatively less dominant. And that's all I have. And if you have questions, we can discuss. Thank you.
Thank you, Boyin.
Yeah.
Yes. So a round of questions to the speakers. Are there any questions or comments or anything? Yes, a few. The audience here.
Hi, I'm Ruben from Barcelona, ECM. I just wanted to ask Boyin about this last conclusion, about the decreasing trend of extreme SST events. The next slide. Well, it's represented here. No? Well, it's okay.
Yeah, maybe
about the record-breaking SST. I just wanted to know your opinion, if you have any opinion of why this may be happening.
These two things. First of all, if you just look at the supermagnetic heat wave, for example, first panel, I believe it's still sharing. So if you look at the red line of the first, it's still increasing. So magnetic heat wave, like record breaking, is still happening and increasing with time. But the key here is the reference, the ratio relative to the extreme magnetic heat wave, the black line. Yes, red line is increasing, but the black line increasing faster than the red line. So this causes the ratio actually becomes decreasing. So I think it's kind of a little confused. First of all, it's absolutely the magnitude is increasing with time, or the increase very weak, but the ratio is definitely decreasing.
Right, thank you.
Yeah.
Yes, Salvatore.
Hi, thank you for the presentation, very interesting. I have a question about the method used for the trending. And you know, actually there are several methods proposed in the literature for the trending. What method you use if you think that there is choose a method rather than another, make a significant impact on the estimate. And second question is, have you investigated how deep heat wave can penetrate into the ocean? Because this is important, of course, for the heat content in the upper ocean.
Did you get the question, Boyin?
I've got a question a comment for Chris and a question for Boyin, and then maybe a suggestion depending on his answer. So, Chris, can we bring up Chris's slides? I think you've missed one aspect of your analysis. So it's a comment that you might want to just comment on or whatever. You're using SST to measure the trends, climate trends. The SSTs, especially seeing as they're getting very hot in many places each year, have a theoretical maximum. The maximum is driven by when the fluxes, incoming fluxes equal the outgoing fluxes. This doesn't happen very often in the past, but it happens quite a lot now. And obviously that equilibrium is driven by the chemical makeup of the atmosphere. Up until so this is just my experience on the Great Barrier Reef. Up until 2016, you could plot SSTs across the Great Barrier Reef and almost draw a straight line across the maximums that existed from time to time. Not all years get to their maximum, and not all pixels make their maximum. In 2016, it jumped rapidly. And if you go backwards until we see even that graph that we can see up there will do.
Go backwards. Oh, that doesn't work. Okay.
Just one of those graphs, that'll do. it showed up in a lot of graphs that both of those graphs there. That'll oh, no, go back to one of the others. Yeah, that'll do. So you notice that in 2016 it jumps, and then it's sort of a little bit stable, but still going up in terms of the peaks. Now I know this is more of an average than what I'm talking about, but I wonder whether or not the chemistry of the atmosphere changed dramatically, and I wonder whether it's associated with melting in the tundra and the release of methane into the atmosphere. In other words, has that maximum theoretical temperature increased all of a sudden?
This is
If it's green, yes.
This is using those two SSTs to predict the cloud radiative effect in the shortwave. So what we're looking at is effectively a measure of albedo in the tropics here. I think your experience in the Great Barrier Reef is, it's the sort of thing that can happen if you look in one place. Whereas what matters for the whole tropical circulation is really the contrast between the warmest places and the average. That's why SST hash is not defined for a particular place. It sort of moves around, always around the warm pool mainly, but it's the way it's defined, it's really not dependent on looking at one place and seeing how it varies over time, because you just take the warmest 30% of the whole of the tropics, because that's what's driving the convection. And so if you look at an average like that, you don't get the sort of effect that you're talking about if you just look in one region.
Okay, so my other is marine heat wave related now. So Boyin, did you you integrated across a calendar month for most of the tail end of your talk? Is that right, for the marine heat waves?
Yes.
Okay, so I have a suggestion that I think might improve your results. The Southern Hemisphere, in the Southern Hemisphere, if you've got a significant marine heat wave, it will straddle to 2 calendar years. So you are better off potentially defining a different year for marine heat waves in the Southern Hemisphere versus the Northern Hemisphere. And you might even choose to have a different year altogether for the tropical band. I did a similar analysis, not with marine heat waves, but certainly with degree heating weeks products, and we defined a new year for the Northern Hemisphere and a new year for the Southern Hemisphere. They somewhat overlapped, but what we did was we looked around and asked the question: when is which part of the year has the least anomalies, and therefore we'll call that the pseudo winter, and we'll go from there to the next year, and that's our calendar year. If you do that, I think you'll find that the results in the Southern Hemisphere will change significantly and start to maybe even match some of the results you're seeing in the Northern Hemisphere.
So you mean that define like Northern Hemisphere like summer year and versus the Southern Hemisphere summer year, right?
Yes, I mean use seasons to seasons. Just
but
take away the calendar. Define a year based on your anomalies, not on the calendar, because the marine heat waves don't care about calendars. They don't even know about it.
I'm not quite understand. Maybe can you send me your email or your reference? That will be for me better to understand. Because what we did is a different calendar year or calendar day of the during a year. For example, July 1st. So July 1st is in the Northern Hemisphere is summer, but in the Southern Hemisphere is winter. So particularly for July 1st, we look back historical record, like from 1982 all the way to 2024, for example, for the marine heat wave 2025. Then we look for the record-breaking SST. Which year happens, we don't care, but we look at the maximum SST as the reference. Then we compare with the July 1st, like 2025, whether it's record-breaking or not. So that's what I did.
Okay, so you mean you didn't use the calendar year, you defined your year based on the data?
Yeah, but the record reference is evolved from January 1st to December 31. So every year, every day of the climate, like climatological day, it changes. If we look at this one, for example, the I'm not sure I still shared. So let me share this one. So this red line represents the record-breaking SSTs. So this record-breaking SST evolved from January to December. It changes. So in this case, in the northern hemisphere, certainly the record-breaking is in the summer season, but it could, I mean, happen in the winter season, like in the northern hemisphere, for example, January or somewhere. But in the southern hemisphere, if you look at these examples, I believe this happens maybe in January or February or things like this.
Okay, so you've ensured that the continuous marine heat waves like this are contiguous in your analysis and not split between one year and another when you're presenting that data.
Oh, the events, for example, from December to January, what you're saying, across the year, right, period, right? So record-breaking SST always calculated the start from 1982 all the way to the last day of the data period. So record-breaking or other marine heat waves is not like calculated always started from January to the end of the year. So this is, I think, some people maybe, if you're doing the marine heat wave, you have to pay attention about this like year change from December to January. So I have to load all the SST from the first point, like January 1982, all the way to, for example, December 31st, 2024 as a time series. Then you look at the events, whether SST has satisfied the criteria. Even between December and January, you can have like one event, no separations, without any separations.
Okay, I think you've covered what I was thinking about. Thanks.
Yeah.
You can
add
continue.
something about this point. We have studied in the ESA project of Kerit all the statistics of marine heat wave and making also evaluation of different choice of threshold and the definition of climatology that has a very important impact on single event, a single area coverage of the system. So my impression is that perhaps we should revise completely the methodology of definition marine wave. We will have a meeting in October organized by ESA from our project to discuss this point and to provide the outcome of this meeting workshop will be to write a white paper on what is the status of the marine wave and how we should revise the definition of the marine heat wave. And there is another point that I think is very important to consider. We know exactly, there are 2 points very important to consider. We have know exactly, and this presentation is clearly seen and also your presentation that we have an increase in temperature in the last 40 years and also before. So the approach that we use for definition of marine wave that is considering to have a mean that has sense, obviously, if your system is stable, not is included the trend. So this is important point to remove. In our project, we decide to have two different classification marine wave with trend and without trends. But the important point is that this depends also on the impact we want to use. Obviously, if I want to look to an impact on a marine species, the important point could be the maximum value of temporal reach, respect an anomaly. So my discussion here is that perhaps we should, it's time to look again on the definition and try to find a better way to define marine wave.
Yeah, I think this is a very good comment and suggestion. I always have problems of the marine heat wave criteria at 90 percentile. So I always try to talk to my colleagues 90 percentile or like 90% like standard deviation. It's very easy to reach. So that's my feeling is, yes, we need to actually redefine the marine heat wave, like your different climatology or references. So I think it's a very good point.
Okay, thanks. Thanks for all your questions and comments. I think this is the last point is actually, I think, leading into the taking us into the next topic, which is sort of the discussion on GRIS priorities. But thanks for the bridging, Leah. So we now had these 5 excellent presentations on global CNCI surface temperatures, climate data records, indicators, and so on. Maybe we should bring it up. Here we go. Well, yeah, just the slides. So we have now, let's see how much time do we have left, Owen? 10 minutes or something like that. 7 minutes left to reflect on the GRIS priorities along these lines. I mean, and what should we focus on in the GRIS science team in the SST community, and where are the things that needed to be coordinated? And yeah, of course, that's Leah. You brought something up. I think that's let's start with that maybe. If there is a need or a wish for something to be coordinated here, or how should we do that in terms of, I guess, marine heat wave definitions and the impact of making different choices when you calculate the marine heat waves, because that's I think there are some ongoing activities within several projects and as I can see it, and both in Europe but also worldwide, and there is a huge interest in these in the results. So you brought up this was it a workshop in October, or you had some initiative, or you had some projects? Maybe tell the mic. Sorry.
We have decided to have a workshop at ESA as a part of the discussion in order to make a point what is the status of marine wave. I think this is an important point also for Greece. So we could think that the results of the workshop can be part of the Greece activity and the discussion. We have a limited number of persons that are invited to the workshop because we want to have a working workshop instead to have a real conference in some sense. But and so we already sent the invitation to what we thought would be the person to contribute to this point, but is obviously open to the discussion. And I think it's really a time to understand what is important, especially if we look to the potential impact of marine waves. That is, and our project is also trying to investigate the propagation marine waves. I'm sure to come here, otherwise I will make a presentation of the project. Salvatore yesterday said that there is a poster of this, a virtual poster of this, but if you want, we can perhaps during the year when we have this meeting online to provide an overview of what was happening, and especially what could be the outcome of this workshop that we are proposing, planning to have in October at ESA.
Thanks. Yes, I think that's and as the GPO, I mean, we're happy to facilitate and disseminate all results to the science team from such a workshop, and also if other activities. I think there was a white paper which is also in production on marine heat waves and so on.
Yes, the idea was as outcome of the workshop to write a community paper on this point. And obviously, the workshop is a moment. GHRSST is something that is stable for a long time, so we could also think to have an action as GHRSST that and consider the workshop as a starting point of this action.
Yes, and
establish a group working on marine wave.
So I think, thanks for bringing it up. I think what we should do now is, that's a topic, and we can discuss in coffee breaks and throughout the week. And we have also 15 minutes on Friday to sort of wrap up and say, okay, so what do we really want to do about this? So we don't have to solve everything now, because I think there are other topics in terms of priorities. Maybe, Christina, you have a short comment on that?
So I'm Cristina from the Marine Science Institute, the SIC in Spain. I mean, I do agree with what Leah pointed out, and you will see on Ruben's presentation, we are kind of saying kind of the same. But something related, it could be related than just taking back the presentation from Ursula. No, I just forgot Mercator. Karina von Schuck, something impronounceable for me. So I think that another key point would be that as Greece and as a community, we should somehow, I think you pointed out to her the question, how are we going to define which is the criteria for the global warming indicator? Because I don't know if they are going to point out this kind of marine heat wave, and there, I do agree we need to redefine and to be clear and to point out all the things that Leah pointed out. So I think this would be another priority for the Greece community as well.
Yes, thank you, Christina, if I also comment. That was also on my list. I mean, because that's, I think that Christina is representing a fairly large user uptake community, so within the Mercator Ocean, and looking at these indicators, and so she's looking at GHRSST for us to guide them on how to estimate the global sea surface temperature in a proper way, and how to deal with uncertainties, how to calculate it, and also, as I heard it, she also would like some, I don't know if we are the proper body to do that, but some guidance with respect to the reference periods in the late 18th century, and because a lot of debate is going on in terms of the 1.5 degree offset, but that's probably maybe, I don't know if there are any comments on those topics, what fits into GHRSST and what doesn't. Should we do something about that?
Well, I can say something about what the air surface temperature people are doing. They're doing a community paper on how to define global warming for this 1.5 degree Paris target, so that is an ongoing activity, and they're facing this question that they have the long term, but they also have lots more information in a more recent period where they can do a better estimate. And I think they are defining one of the options they're looking at is is to separate out the problem of 1850 to 900 up to some reference period that's more recent. And that's one transformation with it, or that's one change with its uncertainty. And then looking at some reference period like the 1980s through to 2010 to the modern day. And that's another step. So they're breaking it down that way. So clearly the GRIS community could have an opinion about both of those periods, but our day job is more related to the second of those two problems.
Mm-hmm. Great, agree. Jorge, you have a hand raised. Go ahead.
Yeah, thank you. Just a quick comment. In terms of an issue with marine heat waves, also, I'll be presenting something tomorrow, but I also think the issue of resolution should be part of the discussion also.
Yes, good point. Okay, is there good topics? Let's continue. Let's continue in coffee breaks to discuss. I think these are at least two identified items. Anything else? Otherwise, it's fine, and we should probably move on and change chairs. I think, right? Salvatore and Claudia. Yes. So yeah, big hand for the speakers. You don't